The genius of the British race is exemplified not only in its great poets and playwrights, but also in the men in the shops and drawing offices. Britain's industry depends on her craftsmen. The wheelwright, the man who makes wheels. The shipwright, the man who builds ships, whether he works in wood or in steel. And now the Tubewright, a craftsman in tubular steel structures. Most people think that tubes or pipes are used only to convey fluids and gases, but the steel tube is also an ideal structural member. There is nothing new in tubular construction. Nature herself, that unrivaled engineer, provides the best examples, and always uses hollow structural members where compressive or buckling stresses occur. An ear of corn is supported by a tubular stalk. The weight carried is relatively large, the center of gravity high up, and stresses due to wind can become severe under storm conditions. Birds are another example of how nature has dealt with the problem of weight saving combined with maximum strength. The quill of each feather is a thin-walled tube, subject to heavy stresses due to its being cantilevered or supported at one end only. The great engineers of the 19th century well knew the advantages of the hollow section. Robert Stephenson in 1850 built the tubular bridge over the Meani Straite in the form of two tunnels in rectangular section made of wrought iron plates riveted together. Rectangular section. For of course the hollow section need not necessarily be circular. For more than 100 years this bridge has carried an increasing weight of rail traffic to Anglesey. The fourth bridge, built in 1889, was at that time the largest bridge in the world and is a fine example of the use of the round hollow section. It was constructed from rolled steel plates, formed into tubes and riveted like an old-fashioned boiler casing. Nevertheless, despite these impressive examples, little headway was made in tubular steel engineering, owing to the difficulty of making cheap and efficient tube-to-tube connections. Stewart and Lloyds were naturally among the first to use steel tubes for constructional purposes. In 1906, they built the roof trusses of their Clyde offices from tubes with screwed and bolted connections, and issued a catalogue dealing with this use of the steel tube. But for nearly 40 years there was little progress in this branch of engineering, as the problem of joining the tubes efficiently and economically still remained. However, just as the advantages of bamboo as a structural member in scaffolding were known throughout the East, so the strength of the steel tube with various types of mechanical joints has been utilized for many years for scaffolding in other parts of the world. In many places, tubular scaffolding has taken the place of heavy balks of timber to shore up buildings. Hundreds of miles of steel tube were used along the Coronation route for seating and stands, where the safety factor was so important. Safety of a different kind has been secured by using the strength of the steel tube to combat coastal erosion. 3-inch steel tubes with spacing girders top and bottom trap the stones and shingle, and in the course of time, the sea builds up its own breakwater. In cities and towns everywhere, steel tube is extensively used for lighting columns and other street furniture, as they call it. Temporary islands and barriers of tubular steel are light yet strong, easily moved and stacked for transport. Nearly all coach and bus shelters, too, are tubular structures. Ships' masts, derricks and booms are an application where the strength compared with the weight of the steel tube is used to full advantage. This factor of strength with lightness was put to good use during the war in bridge building. The Ingalls Bridge was made from steel tube with mechanical joints. The experience gained in the use of steel tube as a structural member and the great advances in welding technique and equipment enabled the Tubewright at last to join tubes efficiently and cheaply. This opened up a wide field For instance, in new types of bridges, the Brook Bridge, welded up in tubular steel units, can span nearly 60 feet without intermediate support. And the Usk Bridge, which can span up to 120 feet, is built up from standard welded units. A big advance was the Southampton Car Bridge, the first pontoon bridge of its kind in the world. This bowstring bridge was erected on the dock side and then lifted bodily into position. These light all-welded bridges can be erected speedily and easily on the site and point the way to the future. Another wartime development, which has reappeared in civilian guise, is the tubular steel servicing platform, providing light but rigid steps. And a hydraulic platform which can be adjusted to varying heights for servicing aircraft in the jet age. From service platforms to railway gantries. In the electrification of the British railway system, steel tubes are used experimentally in place of angle sections because of their high strength-to-weight ratio. But it has been standard practice for some years in the design of crane ships, such as this luffing crane in the London docks. For all types of materials handling gear, too, the steel tube is eminently suitable. Tubular steel crates and stillages have been designed for many trades. For instance, at the Manhattan Works of Jute Industries Limited, Dundee, the most modern jute mill in the world, yarn and cloth are moved along the production lines by stillages for the flat, easily stackable items, and crates for awkward loads such as the spools or cheeses. Not only does this type of equipment provide efficient handling on the floor, but its strength and lightness make it most convenient for interworks transfer of materials. Moving materials from floor to floor is just as easy with these crates. A bar through the top, lifting gear, and the trays of cops arrive at the looms. As in other industries, continuous production requires an uninterrupted flow of materials. Feeding these circular looms is facilitated by this equipment. Below the looms, an unusual type of stillage holds the endless tube of cloth before it is cut into sack lengths. This type of equipment is made up from tubes welded in permanent form, as the materials in this mill do not vary in shape or size. Where the materials differ in shape and size, Tubewrights have devised the patent demountable pallage system. The assembly of the standard components is simplicity itself. With a deck, feet, studs and domes, a stillage can be assembled. Or with 4 posts added, a post pallet. A rack is made by the addition of another deck and further posts, or with side and end panels, crates, to meet all factory requirements. In their motorcar division, Rolls-Royce have adopted this new pallet system. Every lathe and machine has its own type of pallet to hold the completed work for inspection and examination. The type of pallet or crate varying according to need. In these Rolls-Royce stores, there are 29,000 different kinds of spare parts and components, all stacked in the minimum of space, yet instantly at hand whenever required. Carried by a stacking truck, the flanged feet position themselves simply and accurately. Pallet units can be made up into post pallets of different designs, which are stacked at easily accessible points around each particular job. The use of the hollow section in the form of steel tube is comparatively recent in this type of equipment, but already, in addition to the motor industry, it has been widely adopted for the food, electrical, public transport and heavy engineering industries. Post-war housing demands led to other advances in the use of steel tubes, this time for building frames. 165,000 tubular trusses were supplied for these prefabricated houses. From the experience gained in this class of building came the Archon range, which has contributed to the extraordinary post-war development of British exports of prefabricated buildings. The Archon tropical building has been erected in 78 countries. One of them recently withstood a 170-mile-an-hour hurricane in Fiji. This type of Archon house was designed for workers in the world's oil fields. Another interesting structure is the three-pin frame shelter. Its attractive lines give it a cool and airy appearance. The sawtooth roof, admitting natural light for factories and works, is also produced in the Archon range of buildings. Another range of buildings designed in many ways on similar principles is the Unima. Let the erection of a standard Unima building illustrate the typical methods of assembly for buildings of this type. The site is marked out and the foundations laid. All the materials are prefabricated at the works and are sent by road to the site. For convenience of transport and handling, the 33-foot trusses arrive in two halves, with center ties loose, and are assembled by first bolting the two main halves together. Then, the main tie is completed by bolting in the center tie. The sag tie is then bolted between the apex plates and to the center tie. A Unima building can be easily and quickly erected by 3 men, using the simple tackle available in any builder's yard. The first 33-foot truss is hoisted and held, while the supporting column is reared and placed in position on the concrete base. Then, the first truss is shored up with poles, and the second truss partly hoisted. A stud is screwed into the eaves purlin and joined to the truss by a loosely threaded nut to give play during hoisting and freedom for the purlin to turn at one end while being screwed to the truss at the other. The purlin is lifted by a hand line and bolted to the shoe of the first truss. The use of continuous and rigid purlins forming a tie from end to end allows in most instances the omission of the usual wind bracing members, with a consequent saving in cost. The loosely threaded nut holding the purlin to the previous truss is now unthreaded, and the next purlin is married to the previous one. It took 3 men 11 hours on the site using ordinary builder's yard tackle to erect the tubular framework of this Unima building. A more elaborate type of prefabricated building is seen in the new factory for Rotax. It was the first all-welded tubular steel frame building in Great Britain. The 40 and 60-foot trusses were prefabricated and sent by road transport to the site. The columns were also sent by road. With the exception of foundation bolts, no bolts or nuts were used in this structure. Even the temporary bolting normally required before welding was unnecessary. Semicircular cleats were welded onto the columns to provide self-aligning locations to support the trusses during fabrication. To give an even distribution of natural light, the design called for a monitor-type roof. The monitor frames were welded to the 60-foot trusses on the site. Ready for assembly, the truss is hoisted by a light mobile crane, and with a minimum of maneuvering, fits into position. The other half of the cleat is placed over each of the truss ends, and the whole welded to the supporting column. The saving in steel was considerable. Only 450 tons were used in this all-welded steel frame building of 8 bays, covering an area of 165,000 square feet. It was erected at the rate of a bay a fortnight by an erector in charge, 4 welders and 9 other men, 14 in all. The symmetrical lines of the tubular sections and the delicate proportions of the trusses generally produce a pleasing, lightweight appearance. A A large factory building of a different type has 80-foot tubular steel trusses incorporating lantern ventilation. Unlike the trusses for Rotex, these were not prefabricated at the works, but were built on-site in jigs erected for the purpose. For ease in handling, the trusses are first welded as halves. Then, after painting, the two half trusses with flanged ends are bolted together. From the fabricating site, a crane easily swings the truss into position for assembly. The surface area of a tubular structure is, on the average, between 30% and 40% less than with rolled angle sections of equivalent strength. This is an important consideration, as due to the smaller surface area, there is a considerable saving in painting and maintenance. The overhead traveling cranes for this factory show yet another advance in the use of the steel tube as a structural member. 18 cranes were built at Corby in the shops in which they were to work. Apart from the angle traveling rails, the framework was of tubular members, which gave greater rigidity and strength, and reduced the weight of the cranes by 25%. The lighter framework meant that the total loading was reduced. Savings could therefore be made in several ways: in the size and horsepower of the motors to drive the cranes, in the power consumed, and in the steel used in the supporting gantries themselves. The motors and mechanical gear were fitted, and the cranes put to work to handle loads up to 7.5 tons. A handling problem of a different type was presented at a steelworks where it was decided to build a new blast furnace just where an existing skip bridge was put in. The problem was to erect a new skip bridge in such a way that the two existing blast furnaces could keep at work without interruption while the old bridge was being demolished. Working in the constricted space between the furnaces and the stoves left little room for maneuver, but by fabricating the tubular framework vertically, the new skip hoist could be quickly mounted with a minimum of interruption to output. The right-hand tubular girder, still held temporarily in its vertical position, is ready to be lowered on its anchor swivel pin. The tubular girder is lowered until it rests in its location at the top. When in position, the girder is pinned. Apart from the pins, top and bottom, the entire job was completely welded. Some of the welds had to be run 80 feet above the ground. Within a matter of months, the new bridge was working and the skips busy charging the blast furnaces. With the old bridge demolished, work on the new blast furnace began. Tubular steel engineering in the field, of the order of the skip hoist, was again a modern development, but was not possible without a great deal of experiment and research. Welders had to be taught the new techniques, and the experience gained was soon applied to more ambitious engineering feats. At Scunthorpe, 2 new conveyors were built to shift overburden from one side of the quarry to the other. Each was built of steel tubes on the site, and each rests on 3 bogies which traverse up and down the quarry. A section, lowered over the vertical projection on the rear bogie, completed the framework of the undercarriage. Then the rear section of the conveyor was positioned above it. At the forward end, preparations were made to raise the boom, which was constructed on the ground and then moved with its tip resting on the spoil bank, ready for hoisting. The 150-foot cantilevered conveyor boom was easily raised at the correct angle. Guide rods on the 4 main boom members facilitated the final positioning. These overburden conveyors were designed to shift a clay soil which does not need blasting. The problem presented in the iron ore quarries at Corby, where the overburden of limestone and rock does need blasting, called for an entirely different kind of machine. The solution of the problem was in the design of the great jib for the largest walking dragline in the world. The answer again was to use steel tube, to get the weight in the bucket and not in the jib. The new welding technique and the production of a new high-tensile chrome molybdenum steel that was easily weldable made it possible to design and construct a 282-foot jib, built entirely of tubular sections and welded entirely on site. Already several machines similar to this great walking dragline have been ordered, and great strides have been made in the use of tubes in structural work, particularly in steel tube cut and fabricated on site. The pioneers of this type of construction are Tubewright Limited, a subsidiary of Stewart and Lloyds, established to develop the use of steel tube as a structural section. At Liverpool, Tubewrights built a large new factory in 1953. Naturally, it had an all-welded tubular steel frame, and adopting the new engineering technique, all columns and trusses were shaped, welded and erected from plate. Columns were 16-inch seamless steel tubes and weighed about 1 ton each. A cap and collar assembly carried trusses and the lattice girders. Here again, the only bolts in the entire structure were those used for aligning the columns on the foundations. The lattice girders are 120-foot span. 21 of these were made from 8-inch tube, welded in jigs on the site. Each girder weighs 6.5 tons, and the average time for positioning was 7 minutes. "415 tons of steel tube were used for the framework of the factory, which covers 141,000 square feet. There is not only a saving in steel, but a corresponding saving in transport, foundations, erection, and labor costs. Only 30 men were employed, and the time taken to complete the entire framework was 4.5 months. Sealing the tube ends by welding prevents the collection of moisture or dirt inside the tube and eliminates the danger of internal corrosion. A section cut from a tubular truss, erected nearly 50 years ago, showed no signs of corrosion. Brickwork combines particularly well with tubular sections. The bricks form hollow pillars round the columns, and the spaces are filled with concrete. The roof is covered with aluminium sheet, insulation board, and layers of felt. Any other type of cladding is suitable. The new works will be used for the mass production of tubular steel roof trusses, bridges, jibs, electric railway gantries, transmission and floodlighting towers, materials handling equipment, and other structures for a wide variety of purposes. Day by day, Tubewrights dispatch consignments for shipments abroad and for new factory and engineering sites in this country. Using steel tubes of the best quality, employing the skill in design of specialized draftsmen, backed by continuous research and development, the Tubewright has advanced from being a pioneer, learning from nature, to become a craftsman. Progress has been remarkable, and there is a great and expanding future in all types of structural work for tubular steel engineering. And this is only the beginning.